Hi. Today I want to attempt to derive the relationship for Ehrenfest theorem, especially the one relating to the time derivative of momentum to that of the force, or more specifically the time derivative of expectation value of momentum to that of the expectation value of the negative gradient of potential. So the Ehrenfest theorem is important because it gives us a relationship which we can trace back to the Newton's second law, which is one of the fundamental pillars of classical mechanics. So if quantum mechanics is a more general, more true theory of the physical world, then it should also be able to explain the classical theories or Newton's laws of motion, for instance. So the Ehrenfest theorem gives us a connection to the Newton's laws of motion and to the laws of classical mechanics. So the Newton's law of motion, the second law of motion, which relates the force to that of acceleration or force to that of the time derivative of momentum, is one of the fundamental expressions of classical mechanics. The equivalent expression is given in quantum mechanics by the Ehrenfest theorem. In this case, so the relationship is basically the time derivative of the expectation values of momentum is basically equal to the expectation values of the negative gradient of the potential. So the negative gradient of potential is simply force, the force experienced by a particle in a given potential field. So I want to prove this. That's all I want to attempt in this particular video. So let's start. So the expectation value of momentum is given by if psi is the solution to the Schrodinger's equation for some kind of a quantum mechanical system, then the expectation value of momentum for that particular quantum mechanical system can be written as psi star p cap psi dx from minus infinity to plus infinity. Of course, I am trying to attempt to do this for one-dimensional motion. So the particle, if assuming is restricted only to the x-axis, in that case the expectation value for momentum can be written in this manner, where p cap is nothing but the operator for momentum, which is minus I h cross del psi by del x. So let's attempt to put p cap here in this expression. It becomes minus infinity to plus infinity psi cap psi star minus I h cross del psi by del x dx, which is equal to minus I h cross psi star del psi by del x dx. So this is the expectation value for momentum. Okay, now I want to find the time derivative of this expression. So let's make on the side, let's make a sort of a column for all the formulas so that I can come back and look at those expressions from time to time. So the first expression I want to note down is expectation value of momentum is minus I h cross psi star del psi by del x dx. Okay. So the time derivative, the LHS, the left hand side, is equal to the time derivative of the expectation value of momentum, which can be written as minus I h cross d by dt of psi star del psi by del x dx, which is equal to, so I can take the time derivative inside the integral. If I do that, then it becomes del by del t of psi star del psi by del x dx. So as you can see, the moment I take the derivative inside the integral, it becomes a partial derivative, because the wave function can be a function of both space and time variables. So therefore it becomes a partial derivative. If I do the partial derivative onto these two functions, then it becomes minus I h cross. So it becomes del psi star by del t dot del psi by del x plus psi star del by del x of del psi by del t. Now, if you look at the second term here, this is nothing but del by del t of del psi by del x. But since x and t are both independent variables, and in that case we can sort of change the order of the derivative. So if I do a del by del t of del psi by del x, that is the same as if I do del by del x of del psi by del t. The reason I am taking the t variable, I am trying to find the derivative of psi with respect to t first, is because I want to substitute del psi by del t with some other expression which I can obtain from the Schrodinger's equation. So let's note this expression. So let's say that this is expression number 1. Now let's go back to the Schrodinger's equation. So Schrodinger's equation, the time dependent Schrodinger's equation is given as minus h cross square by 2m del square psi by del x square plus v psi is equal to I h cross del psi by del t. The reason I'm coming back to the Schrodinger's equation is that I want to substitute del psi by del t from the Schrodinger's equation here, which would simplify the expression for us. So let's see what I can get. Or del psi by del t is equal to 1 by I h cross minus h cross square by 2m del square psi by del x square plus v psi, or I can take the I to the numerator if I want. So this, then in that case it will become minus I by h cross minus h cross square by 2m del square psi by del x square plus v psi. So this becomes, so if I multiply the constants, in that case this is going to become plus, so h gets cancelled, I h cross by 2m del square psi by del x square minus I h cross v psi. Now if you look at this expression, I also have this expression del psi star by del t. So psi star is basically the complex conjugate of the wave function. So I also want to obtain the del by del t of the psi star. So which is basically I replace psi with the complex conjugate psi star, and then I also replace I with minus I. So I is the imaginary number here in this case. So then del psi star by del t is going to simply become minus I h cross by 2m del square psi by del x square plus I by h cross v psi. So these are all psi star. Okay, these are all psi star. So let's write down these two expressions because I'm going to use them. So let's say this is equation number 2 and this is equation number 3. Substituting equations 2 and 3 in equation number 1. So d by dt of the expectation value of momentum then gives us minus I h cross is going to be long integral. So let's be a little patient. This is going to become del psi star by del t is minus I h cross by 2m del square psi star by del x square plus I by h cross v psi star del psi by del x plus psi star del by del x of del psi by del t, which is I h cross by 2m del square psi by del x square minus I h cross v psi dx. Okay. Now let's separate these two terms and these two terms, because then that would help us solve this particular integral. Let's see what happens if I separate it. So if I separate these terms, then so let's take minus I h cross I take this term outside. So let's take this term outside. So minus I h cross by 2m. In that case, this integral is going to contain del square psi star by del x square del psi by del x. Okay, and I will also want this integral to contain this term. So this term is nothing but so I have taken minus I h cross by 2m. So this is going to be minus psi star del by del x of del square psi by del x square. So this is one integral. I want to separate it into one integral, and the next integral is going to contain minus I h cross these terms. So let's take I by h cross outside. If I take I by h cross outside, I am left with the integration of v psi star del psi by del x. Okay, and so I have taken I by h cross outside. In this case, I have I by h cross, so this becomes minus psi star del by del x of v psi dx. Okay, so obviously this constant can be simplified as minus gets cancelled. I into I is I square, which is 1, h square. So basically this becomes minus h square by 2m. This h gets cancelled. I into I is I square, which is minus 1, that again gets cancelled. So this becomes plus. So now if you look at this particular expression here, this is nothing but del by del x of product of v and psi. So v is the potential field and psi is the wave function. I can simplify it instead of writing a line here, which I think is going to go out of the camera view. Let's just simplify it here. So this I can write down as, so this can be written as dv psi minus psi star v del psi by del x dx. Okay, I think this can be written in this manner. So if you look at the first, in the second integral, inside the second integral, this is the first term is v psi star del psi by dx del x, and the third is v psi star del psi by del x. So these two terms gets cancelled, and the only term that is remaining is this one. Okay, the only term that is remaining is this particular one. So let's write it down again. So this term, if you look here, this term is nothing but integration of minus integration of psi star minus del v by del x psi dx. That's all. So this term is nothing but the expectation value of del v by del x. So del v by del x is the gradient or the space gradient of the potential field, which is nothing but the force experienced by the particle. So I'll just, not this expression, just a normal bracket here. So this is nothing but the expectation value of minus del v by del x. So let me write the expression again. So del by del t d by dt of del t is equal to minus h cross square by 2m integration of del square psi star by del x square del psi by del x minus psi star del by del x of del square psi by del x square dx plus the expectation value of the negative of del v del x. So as you can see, this term already comes from the second integral. So inside the second integral, the first and the third term gets cancelled out and only the second term remains. The second term is psi star minus del v by del x psi dx. So this is the expectation value. This is how the expectation values are defined. So you sandwich the sort of operator between psi star and psi, and then that basically gives you the expectation value of that particular physical quantity. In this case, the physical quantity is del V by del X. So I'm going to write it here. Now let's look at the first term. So what happens to the first term? That is what we need to do now. So if you look at the first term, first integral, in this first integral there are two different sort of terms. So let's look at this particular term first, because I think that is going to help solve. So this is star. This is going to help solve the expression quite easily. So let's look at this particular term. So which is the second term inside the first integration. So the second term, so this expression is psi star del by del x del square psi by del x square integration dx. Okay, this is basically the second term inside the integration. Okay, if I separate it. Now let's see what we can do about it. So this contains psi star, and this also contains this del by del x of del star psi by del x square. So this can be separated or by doing integration by parts. So what you can do is psi star del by del x of del square psi by del x square dx minus del psi star by del x integration of del by del x of del square psi by del x square dx and dx. Okay, so this becomes psi star. So this, as you can see, so this is del by del x of del square psi by del x square dx. So basically this dx and this dx can be removed. You end up getting integration of del square psi by del x square. So once you integrate it, you end up getting del square psi by del x square, which goes from minus infinity to plus infinity. And here you have del psi star by del x. And again, same thing. So this is del by del x of del square psi by del x square dx. So this dx and this del x can, they remove each other, and you end up leaving with del square psi by del x square, which once you integrate, you end up getting del square psi by del x square dx. Okay. Now, when we talk about wave functions of quantum mechanical systems, then the Schrodinger's equation can give us a lot of wave functions which are unrealistic in nature. So those mathematical functions where certain conditions are not met cannot be used as representations of wave functions. For example, so these leads to certain limitations on the nature of wave functions that we use to represent physical systems. So one of these criteria is that the wave function must always go to 0 as x tends to infinity. So that means psi must always go to 0 as x tends to plus minus infinity. The reason is that the wave function has to represent some kind of physical particle at the end of the day, and if the psi has some finite value at infinite distances, that means the wave function would be non-normalizable, and when you do psi star psi dx, the probability of finding the particle would not give us any meaningful information. So one of the limitations on the wave function is that the wave function as well as its derivatives must always be 0 when x goes to plus minus infinity. So because of this reason, the first term, this psi star, the first term here goes to 0. So this particular term goes to 0 because of this particular thing, that the wave function must always approach, and its complex conjugates must approach 0 as you approach infinity. So you're only left with this particular term here. Okay, so now we want to replace this term here. So let's rub all of this. Okay, I want to replace this particular term here. So this can be written as minus h cross square by 2m integration del square psi star del x square del psi by del x. This is minus del psi star, the integration sign is already here, del x del square psi by del x square dx plus expectation value of. So we have simplified the second term inside the integral with this particular expression that I just now obtained. There is a plus sign here because the moment you take this inside, There is a minus sign here, the minus minus becomes plus. Now, to simplify this expression, all you have to do is minus h cross by square by 2m del by del x of del psi star by del x del psi by del x dx plus minus del v by del x. That's it. This expression is the same as this one. As you can check for yourself, del by, which is the same expression in the first bracket. So this can be written in this particular manner. Now, if I can write it in this particular manner, so if I integrate it, so you see this is a del by del x of this particular expression dx. So this dx and this particular dx, it vanishes and you are left with del this expression, right? So if you integrate it, then this expression becomes this multiplied by this going from minus infinity to plus infinity. That's all. Now, as I already told you that the wave function solutions of the Schrodinger's equation has certain limitations for them to be used as solutions for realistic particles. One of the limitations is that the wave function has to go to 0 at infinite distances, and their derivatives also has to be 0 at infinite distances. If the wave functions themselves has 0 value and their derivatives also have 0 value, in that case this particular expression also goes to 0. You see, this particular expression also goes to 0 and you are only left with minus del v by del x, which is the Ehrenfest theorem. Okay, that's it. This is the proof for the Ehrenfest theorem from the Schrodinger's picture. Okay, so this basically gives the time derivative of the expectation value of momentum with the expectation value of the negative gradient of the potential field, which is very much similar, as you can see, to Newton's second law, which relates force to time derivative of momentum.